Hi everyone, welcome to Random Thoughts with Alex. 3I Atlas is the third interstellar object observed inside the solar system. At the time of recording, late August of 2025, it's making its way towards the planet Mars in a retrograde trajectory. There are a number of peculiarities associated with this object. On August 17, 2025, the Harvard astrophysicist Avi Loeb came up with a particularly unusual hypothesis about 3I Atlas. It produces its own light. Now, let's take a look at Atlas on the left and compare it with its predecessor Borisov on the right. Borisov, which appeared in the solar system in 2019, is undoubtedly a comet. Atlas is assumed to be a comet, but an unusual one. As you can see, Borisov has a small visual core. By that, I mean that there is a small area in the image where the light is oversaturated, whited out. Around the visual core, there is a large field of reflected light where the intensity declines gradually with the distance to the core. The visual core of Atlas is much bigger and the field of reflected light is relatively small. The light intensity drops off rapidly with increasing distance to the core. This was also observed by a group of astronomers including David Jewett from UCLA. They pointed out that this would be typical of a coma consisting of ice particles that sublimate in the sunlight. In this case, that could be CO2 ice, also known as dry ice. Avi Loeb looked at the result and offered an alternative explanation. The coma may be illuminated by the object itself rather than by the sun. In other words, the object is producing light. This would also explain why it is so bright. Alternatively, we must assume that the object is very big, too big to be a common object in interstellar space. Needless to say, an interstellar object that produces light is a very unlikely explanation, so it would be worth if we could produce a testable prediction from that hypothesis. Is there a prediction that could be tested with simple, readily available data? It turns out that there is. So far, I haven't seen anyone mention this, so I did the test myself. An object that produces its own light should have a brightness that is inversely proportional to the distance to us squared. It may have a stronger dependence because we expect the coma to grow as it gets closer to the sun. But if it has its own light source, it stands to reason that it also has its own heat source. So we don't expect that factor to be very important. So let's assume that any dependence of the brightness on the distance to us or to the sun to the power of -3 to -4 is consistent with this hypothesis. That is inversely proportional to the distance to, say, the sun to the power 3 to 4. We are using the distance to the sun as a proxy for the distance to us. What if the object is illuminated by the sun? Then the light power reflected by the object is inversely proportional to the distance to the sun squared, and the brightness as it appears to us has an additional inverse relationship to the distance to us squared. Again, let's use the distance to the sun as a proxy for the distance to us. In that case, the brightness is inversely proportional to the distance to the sun to the fourth power. Add the effect of increasing heat from the sun on the formation of the coma as the object approaches the sun, which is an additional inverse power 2, and we find that we can expect to see a brightness that is inversely proportional to the distance to the sun to the power of 6. Maybe a little less than 6 because ice crystals in the coma will disappear faster when the object is closer to the sun. Let's say of power 5 to 6. In a nutshell, if the brightness is inversely proportional to the distance to the Sun to the power of 3 or 4, it produces its own light. If the dependence is to the power of 5 to 6, it's illuminated by the Sun. I asked Grok to collect all the brightness data of Atlas with the measurement dates. The result is shown here. We see a steady decline from magnitude almost 21 to magnitude about 16 from early May to mid-August. Then I asked Grok to calculate the trajectory of Atlas so that I could plot the intensity as a function of distance to the Sun. A 5 magnitude change in the brightness of a celestial object represents a factor 100 change in the light intensity. Based on that, I plotted the light intensity as a function of the distance to the Sun. The result is shown here. As the distance dropped from just over 6 astronomical units to just under 3 astronomical units, the light intensity increases by about the factor 100. We see that in log scale, the data follows a straight line, and this indicates that the intensity follows a power law dependence on the distance to the Sun. When we use regression to determine the power law, we see that the power is minus 5.5 within the range of the power minus 5 to minus 6 expected if Atlas is illuminated by the Sun, and far from the minus 3 to minus 4 expected if Atlas has its own light source. It follows that, in all likelihood, Atlas does not produce its own light. That leaves us with the problem that Atlas must be very large if the light intensity is due to the reflection of sunlight. It also means that, in all likelihood, the coma we see is due to dry ice particles or water ice particles, not dust, to explain the sharp decline in the coma's light intensity with distance to the object. This seems to be confirmed by the NASA measurements with the Sphere X space telescope taken between August 8 and August 12, as well as by the measurements taken with the James Webb Space Telescope on August 6 and made public very recently. Atlas was slightly over 3 astronomical units away from the Sun at that time. They found that the gas surrounding Atlas is mostly CO2 and that Atlas emits on the order of 130 kilograms per second of CO2. Measurements close to Atlas indicate a much smaller emission rate, 70 kilograms per second or less, indicating that part of the CO2 is emitted as dry ice that sublimates after emission, consistent with what is suggested by the visual appearance of the coma. Analysis of the Sphere X telescope suggests that the object could be as large as 23 kilometers in radius or 46 kilometers in diameter, almost 30 miles. This is based on the assumption that the light comes from the object itself, not from the coma, and that it has an albedo on the order of 0.05, which means that it reflects only 5% of the sunlight it receives. I personally disagree with that analysis. First of all, if the albedo is close to 1, based on the fact that it doesn't seem to emit any dust, then it could be as small as 10 kilometers in diameter. Second, I question the assumption that the coma causes a negligible portion of the brightness. First of all, we know this can't be true because then the power law index should be minus 4, not minus 5.5. So that assumption is off the table. But how do we explain it? We know that Atlas emits as much as 60 kilograms per second of solid dry ice, possibly more. It also emits some water. If we assume that it takes a few hours to sublimate the dry ice, say 10,000 seconds, then there is on the order of 600,000 kilograms of dry ice in the coma, let's say 600 cubic meters. The problem, however, is that dry ice sublimates very quickly, so only relatively big chunks, millimeters inside, can last that long, whereas micrometer-sized dry ice sublimates in a few seconds. However, Water ice can survive much longer at 3 astronomical units. Let's say 6 kilograms of water ice, but lasting 100,000 seconds, so that is still about 600 cubic meters of ice. And let's assume that this ice is in the form of particles 10 micrometers in size. Then, after some math, we find that the combined surface area is 360 million meters squared, or 360 kilometers squared. This is equal to the area of a sphere that is about 5 kilometers in radius or 10 kilometers in diameter. And if the particles are clean water ice, it will have a high albedo. So the coma can explain quite a lot of brightness. I have another reason to believe that the object is much smaller than 10 kilometers in diameter. At a distance of 3.3 astronomical units, it receives roughly 140 watts per meter squared of energy from the sun. Even if we assume that only 10% of that heat goes into sublimating CO2, that is still 14 watts per meter squared, or 14,000 kilowatts per square kilometer. The heat of sublimation of CO2 is on the order of 26 to 27 kilojoules per mole at the low temperatures expected at Atlas's current location. That means roughly 530 mole per second of CO2 sublimates per square kilometer exposed to the sun. That is roughly 23 kilograms per second per square kilometer. So we only need 3 square kilometers exposed to the sun to explain the CO2 emission. A disk with an area of 3 square kilometers has a radius of roughly 1 kilometer or a diameter of roughly 2 kilometers. Based on the CO2 emission, the object should only be about 2 kilometers in size, possibly smaller. I would argue that 90% or more of the brightness of Atlas comes from the coma. 2 kilometers would be a pretty normal size for an interstellar object. What is not normal is that the comet, or whatever it is suspiciously clean. It contains no dust. Maybe that indicates that it originates from the Oort cloud of a star with very low metallicity. It has been argued that Atlas is a very old object, much older than the solar system. That could be consistent with a comet with very low dust content. So there it is. Atlas may be a very normal comet after all, just a comet from a very old star when the Milky Way was not as littered with metals as it is now. Except, just as I'm about to record this, it is found that Atlas emits nickel without iron, which is very suspicious. That is very much like a technosignature. So I guess all bets are still off. I will follow up on this, so more about that in a future video. I hope you liked this video. If you do, please like and subscribe, and I will see you in the next video.